All right, guys, so we're going to talk about one more strategy that we're going to use when we're looking to prove equivalent statements or simplify trig expressions, and that is using difference of squares. So right here, if we're looking at a situation where we've got two terms that are related with the Pythagorean identity, but they're not squared, we can get squares by multiplying by the conjugate. If we look at the difference of squares relationship here, we're saying that if we've got a plus b and we multiply by a minus b, we're going to get a squared minus b squared, right? So multiplying by the conjugate gives us the two terms squared, right? And that's the relationship we're seeing with difference of squares. And that's going to help us in getting squared terms so that we can, use a Pythagorean identity to substitute one term for two terms. So looking at our first example here, we've got secant theta plus 1 over tan theta equals tan theta over secant theta minus 1. Now really we could take either one of our two sides here. I'm going to take the left side. And right here what we're saying is, of course, secant theta and 1 are related in our Pythagorean identity, but that secant isn't squared, so we can't use it, right? So right here what we're going to do now is multiply on the left side by the conjugate over itself. And the conjugate is basically just going to mean switching the sign in between our two terms. So right here I'm going to multiply by secant theta minus 1 over secant theta minus 1, right? Now really this gives me two things, right? I can see that in my target expression, secant theta minus 1 is in the denominator, right? And when I multiply conjugates, I'm going to get my two terms squared, right? So right here, multiplying through in the numerator, we get secant squared theta minus 1, right? And now in our denominator, we've got our secant theta minus 1 tan theta. Now I'm not going to distribute tan through because I know that secant theta minus 1 is something that I want in my denominator, right? So I'm hoping that somehow that tan will cancel out. In our next step right here, we can say that secant squared theta minus 1 is actually equal to tan squared theta. And we can sort of go through and show that with our Pythagorean identities, but for right now, we're just going to take it for granted. And so we've got tan squared theta over secant theta minus 1 times tan theta. And now, of course, in our last step, what we can see is that our tan in the denominator is going to cancel out with one of our two tans in the numerator, and we get our target expression, tan theta over secant theta minus 1. A lot of times, if you can sort of spot that first step, things are really going to fall together for us when we're proving these equivalent statements. Okay, so right here, let's take a look at this next example. Here we've got 1 over secant x plus tan x plus 1 over secant x minus tan x equals 2 secant x. Right here, using difference of squares, multiplying by the conjugate, we're going to get common denominators, right? And we're also going to get squared trig functions in our denominator, which is going to help us use a Pythagorean identity to substitute one term for two terms. So right here, in general, what we're going to say is if I multiply by the conjugate over itself for both of my terms on the left side, right, I'm going to get that difference of squares relationship in the denominator, and I'm also going to get common denominators, which is going to allow me to bring these two terms together. And that's what we want to do, because we can see that our target expression, that simple expression, is really just one term. So right here, what I want you guys to do is to try this out. I want you to multiply by the conjugate over itself for this first term and for this second term, and then see if you can get it to simplify down to our 2 secant x. And we'll come together and look at this in a second. All right, guys, so let's take a quick look at this. Right here, we multiply by the conjugate of the denominator over itself with both of our two terms. So right here, we're multiplying our first term by secant x minus tan x over secant x minus tan x. And our second term, we're multiplying by secant x plus tan x over secant x plus tan x. When we do this, the secant x minus tan x is multiplied into the numerator here for our first term, and our secant x plus tan x is multiplied into the numerator for our second term, and in our denominator we get that difference of squares, giving us secant squared x minus tan squared x for both of our denominators, right? Now we can bring these two terms together and make them one term. So we've got secant x minus tan x plus secant x plus tan x over secant squared x minus tan squared x. Right here, in our numerators, we can see our minus tan x canceling with our plus tan x. And right here for our denominator, we can see with our Pythagorean identity for tan and secant that if we subtract tan squared x from both sides, we get 1 equals secant squared x minus tan squared x. And right here, that means that we can substitute in 1 for our secant squared x minus tan squared x. So we get in our denominator 1, and in our numerator, secant x plus secant x, giving us 2 secant x, our target expression. So again, if you can sort of spot that first right move of multiplying by the conjugate over itself for both of the two terms on the left, then you're kind of, as long as you don't make a misstep with the algebra, you're really sort of just channeled into the target expression. All right, guys, so we'll do a worksheet tomorrow. This is the last of the video. Sorry it ran a little long, and I'll see you guys tomorrow in class.